Okay, what I want to do now in this follow-up video for infiltration is consider what happens in the real world. So remember the result of our ponded infiltration solution. We started with a situation where this is the ground surface here, and we have some amount of standing water, shown by the blue line, on top, and that drives infiltration of water into the ground. And if we look at the moisture content, what we see is that initially we assume that the ground the soil had a very low moisture content given by this line, and that with time a slug of saturated water here starts off small, progressively moves down with time like this. These are different times, thickening that slug of water, and that the rate at which this slug of water moves down decreases with time and eventually reaches a constant rate given by the saturated hydraulic conductivity. So in other words, the rate starts off high and then decreases with time, eventually sort of saturating and reaching a steady state value that's equal to, it's supposed to be a horizontal line out here, that's equal to, if I've drawn this right, the saturated hydraulic conductivity value. So over in here at long time, the hydraulic gradient becomes 1, and the infiltration velocity is equal to, the absolute value of this is equal to the saturated hydraulic conductivity. Now, what I want to do is consider what happens in the real world when we don't have yet ponded water sitting on top of the surface. So let's get rid of this ponded water and think about what happens next. So now we have that uniformly dry soil at the surface, and now the ground is dry and it starts to rain. So here are our little raindrops, our little raindrops falling now on the surface. And there's a precipitation event that's happening at a rate we'll just call the rate of precipitation equals P. That's some kind of precipitation rate, length per time, perhaps inches per hour, for example. And that rate then produces water on the surface, which immediately is sucked in to the soil. However, typically that rate of absorption into the soil, the rate at which that water enters the soil, is limited initially by the precipitation rate. In other words, the initial infiltration rate at very, very low values of L is enormous, and the rate at which water is being provided to the surface by the precipitation rate, I can put it up here on the same scale. This is now P. Remember, everything over here has units of length over time. It's some kind of rate. So now the precipitation rate is the limiting factor in how much water can enter into the soil. So initially what happens is the infiltration rate is governed by the precipitation rate. So initially it stays constant. The infiltration rate stays constant at the precipitation rate. Now what's happening over in the moisture content thing is now this water now is the soil now is starting to fill up, and we start to develop a slug just like we did before. Remember that the rate of downward movement of this slug is inversely proportional to the thickness of the slug. This here is L, right? So when L is very small, the theoretical rate at which this slug moves down is very, very high, and initially that rate at which this slug can move down exceeds the rate at which new water is being provided to the surface by rainfall. And so the rainfall rate is initially the controlling factor on infiltration rate. However, after some amount of time passes, the slug grows to a sufficient thickness here, so this now becomes L, right? Grows to a significant thickness now where the rate of movement of the slug, remember that's decreasing because the distance L is increasing. So the rate of movement of the slug now becomes equal to the rate at which water is being provided by rainfall at the surface here. And from that point onward, the infiltration rate is governed not by the supply of water to the surface, but by the rate at which the slug can move down, which is the ponded infiltration rate equation we showed earlier. So from that point on, at this point right here now, we're saying that the precipitation rate is equal to the movement of the slug downward, governed by Darcy's law. And from that point on then, the rate is going to be governed by the decreasing rate at which groundwater can move down as the slug gets thicker and thicker and thicker. So we follow a curve like this. Now, if water can't flow downward as fast as it's accumulating on the top, what's going to happen? Well, from this point onward, right here, from this time onward now, right there, we're going to start to see water accumulating on the surface, right? Because that water can't infiltrate into the soil as fast. I'm sorry, it can't infiltrate into the soil fast enough. I'm sorry, why am I saying this? It can't infiltrate in the soil fast enough to keep water from backing up on the surface. The rate of infiltration, this rate here, the downward rate, is too slow to keep up with the precipitation rate here. I'll make it a longer arrow. And so as a result, water is going to start accumulating on the surface, and we develop the conditions that we described before, where we have standing water on the surface, and this is the ponded then infiltration condition that we described before. And eventually, of course, this curve will, the infiltration rate will eventually start to slow down when the slug gets thick enough here, when L gets thick enough now to where the hydraulic gradient between the surface and the point right beneath the slug starts to approach 1. And at that point, the downward movement of the slug, Q, infiltration, becomes approximately equal to, absolute value again, equal to the saturated hydraulic conductivity, K. So that's what we ought to see happen in real life when we start with a dry soil without any water on the top and it starts to rain.